Hello everybody, so I'm going to go through the 2017 media paper Christchurch. So let's look at the questions. Okay, let's start off with the first one. 1A, a car with a mass of 800 kg. This is the mass. Starts from rest, so that means the speed initially is 0 meter per second. On a straight road, it has a constant acceleration of 1.5 meter per second square. So this acceleration for 12 seconds. So this is the time it has accelerated at this rate. In 1A, it says calculate the force resulting in the acceleration of the car. So I need to find what's the relationship between force and acceleration, and then it must be a calculation here. So the only formula that you know relating force with acceleration is actually F equals to ma. So I'm able to find the force that I need, okay, if I know the mass and the acceleration, which I have. So 800 kg multiplied by 1.5, what you're going to get is 1,200 Newton. Okay, so that's the answer here. A lot of this, like rest, 12 seconds, is just distractors. It's just whether you know which quantity to start off from and to use. Okay, so next, a van is traveling around a circular track at a constant speed of 30 km per hour. Is the van accelerating? Explain the answer. Now, those speed and acceleration, most of you think that, it's like totally, like, if as long as constant speed, means that my car is not accelerating. So I need you to think about in terms of this idea of circular track. Okay, so before I go on to explain, or van, okay, if I'm going around a circular track, so if the van is in this current position, the direction which the van is heading is this way. Okay, at that particular instant, the direction is in this way. When the van is here, the direction is heading is at this way. Or here is this way. So you realize at different position along the circular track, okay, the van is actually traveling in different direction. Then most of you are thinking, sure, so what's the main point behind this different direction? So I need to know that acceleration is a vector. Okay? And acceleration is actually the change in velocity over time. Now, so there is a difference between velocity and speed, because speed is a scalar, whereas for velocity, it's a vector. Well, I'm not going to write it out, but just take note, speed is a scalar. What is a scalar? A scalar is a physical quantity with magnitude only. That means with a value only. But for velocity is a vector, it means that it has both magnitude and direction. So now, when we talk about the value, so the value of the velocity is 30 km per hour. Okay, 30 km per hour, which is the same as the speed. Because velocity and speed we know is sort of like the same thing. So if the speed is 30 km per hour, the velocity will also be 30 km per hour. However, there's one more thing about velocity that we seldom think about, which is direction portion. So if I'm moving 30 km per hour, so this, and the truck, when the van is here, is actually moving 30 km per hour, okay, in this direction. When the van is here, it's actually moving 30 km per hour. So you see the value is the same, but the direction is now over to this side. At this particular point, it's 30 km per hour still, but it's moving in this direction. So what you will realize is that the value, the magnitude is the same, but the direction is constantly changing. So first things first, okay, how to explain this? So as the track, okay, let's make it bigger. As the track is circular, comma, okay, what is happening is that the velocity direction is constantly changing. So, okay, bracket, velocity is a vector. So please remember that velocity is a vector. The concept of vector is quite important. Hence, sorry, right? Let me erase this out. Since acceleration equals to change in velocity over time, comma, hence the van is accelerating. Okay, so really the key idea here is about the direction part. Okay, I say again, hence the thing here is really about the direction part. Okay, next. Figure 2.1 shows a ruler being held against a rotating tooth wheel. There are 32 teeth on the wheel, and it rotates at 15 revolutions, so 15 rounds per second. Okay, so in 1 second, it will go 15 rounds. Okay, each time a click is produced every time when the ruler moves from one tooth to the next. So one tooth to the next, there will be a sound click. Find the frequency of the click. So frequency is actually the number of times. So you want the frequency of clicks, means number of clicks in 1 second. So I know there are 32 teeth. It will go 15 rounds in 1 second. So number of clicks means actually how many teeth did the ruler sort of like rotate through, and it moves. How many teeth did the ruler move across? Okay, in 1 second. And this is just actually a very simple question. Okay, so frequency is actually equals to, in this case here, there's no formula here, this is about the concept. So 32 teeth multiplied by 15 rounds, okay, what you're gonna get is 480 Hz. So frequency is 480, so it means that it will go past 480 teeth, sorry, per second. Okay, because you hear 480 clicks. Next, the speed of sound in air is 330 meters per second, so this is the speed. Calculate the wavelength of the sound wave. So I want to find lambda using the frequency calculator. So they already tell me I need to use the frequency in part A. So based on this, you realize the formula we're going to use is V equals to F lambda. So V is 330 as indicated above. Frequency is mentioned, we have already calculated is 480, and hence we are left with lambda. Therefore, lambda is actually just 330 divided by 480. So what we're going to get is 0.688. So this is rounded off to 3 significant figure already. So 0.688. Okay, so that's for question part B here. Okay, question 3. The refraction of light at the boundary between air and diamond is shown in figure 3.1. Okay, so it's over here. Now, take note, this is medium P, medium Q, whereas they say it's air and diamond over here. Okay, so before we even start off any question on light, you must always ask yourself, are the angles given the correct angles? Now, how do I know what angles should I be looking at? Take note, the angles are always measured from normal to the light ray, normal to the light ray. Okay, so 20 degrees is correct because it's from the normal to the light ray. But 35 degrees is not the correct angle I should be using. Instead, I should be using 55 degrees over here, because this whole thing is 90 minus 35 is 55. So normal to the. Now, state with a reason if medium P or medium Q represents diamond. Now, I need you to take note, air. Okay, we have already sort of like established that, light travels fastest. Okay, so light travels fastest in air. Okay, I know vacuum is always the fastest, but in your current syllabus, it's taking as it's about the same thing. Okay, so light travels fastest in air, hence it will be slower in diamond. Okay, why is it so? Obviously, because if it's slower, means that diamond is considered optically denser medium. Okay, so state with a reason if medium P or Q represents diamond, the answer would be Q would represent diamond. Why is it so? Okay, so first thing you need to know is that since diamond is optically denser than air, okay, so the keyword is not denser, it's optically denser. So whenever you're doing light question, do take note the word optically is quite important. Since diamond is optically denser than air, hence light will travel faster in air. Okay, so it will bend away from the normal when it moves from diamond, bracket Q, to air, which is P. So you can see here, because the light bends away from normal, I know that in medium P, it must be traveling faster. Okay, that's why I can draw this conclusion over here. Okay. Next, part B. Calculate the refractive index of the diamond. So N goes to sine I over sine R. Now, for those of you in my class, you realize that I don't like to use this formula. I will do some modification here, because to find N, actually what you're using is a sine angle in the air over sine angle in the medium. Now, in this case here, it will be diamond. So, when we talk about this angle here, we are always talking about angle from normal to the light ray. So, we have established that P is air, Q is diamond. So, my angles I should be using is 55 and 20. So, this will be sine 55, because that's the angle in the air, sine 20. Okay, so what I'm going to get over here is actually, if you do your math, you're going to get 2.40 when you round off to 3. Okay, so N refractive index is 2.40. Okay, so this is for question 3b. Now let's go on to the next question, which is question 4. Okay, so question 4. Okay, so let's read through. Figure 4.1 shows a uniform meter rule with a mass of 120 kg, 120 grams. Okay, so suspended at its midpoint. So O is the midpoint. Okay, and the mass of the ruler I know is 120 grams. So what it means that this point O is also the center of gravity, which means that the weight of the ruler is acting here. And what's the weight of the ruler? You need to convert this into kg and multiply by 10. So the weight of the ruler is actually equals to 0.12, that's a kg, multiplied by 10, which you get 1.2 Newton. Okay, so these are some preliminary calculations that I've done. Okay, the uniform ruler, meter rule is balanced with a ball, so it's balanced. That means what I know is that the resultant force is 0. The other thing I also know is that the resultant moment equals to 0 Newton meter. Now, when resultant moment equals to 0 Newton meter, which means that it will be anticlockwise, sum of all the anticlockwise moment must be equal to sum of all the clockwise moment about the same pivot. Right? So these two is the same thing. This one is the next. So, first thing they ask us to do is to calculate the mass of the ball. Then we don't have the weight of the ball. We can't really do anything, right? The only other way is, most probably we need to use moment. Why? Pivoted here. I got the mass, one mass here. I can find the mass over here. Now, but I need you to take note of this. For you to use moments, you cannot use the mass. You need to use the weight. Because moment is actually equals to force multiplied by distance. And grams are masses. It is not a force. But if I'm able to convert mass into weight, okay, can be weight, because weight is the gravitational force acting on the object, right? So if I'm able to convert it to weight, I can do the question. So let's start off simple first. 100 grams, let's convert it to weight. So weight of 100 grams is actually equals to 0.1 multiplied by 10, so it's 1 Newton. So I know that there's a 1 Newton force here. Okay, and what kind of moment will this generate? It will generate a clockwise moment. I know there's the weight of the ball over here. We have the ball over here. The ball over here. Okay, I do not know what's the value of this, but I can calculate it. And this will actually generate an anti-clockwise moment. The weight of the ruler, we can actually ignore it because it's at this pivot. So any force that's on the pivot or cuts through the pivot, actually you can ignore that particular force in terms of generating moments. Okay, you can ignore the moments generated by that force. Okay. So now, using POM, using the principle of moments, what I'm going to do is I'm going to take the sum of clockwise moment equals to sum of anti-clockwise moment. So clockwise moment I know is 1 Newton multiplied by the distance here, 0.25. Anti-clockwise moment, what I have is the weight of the ball, so I put W ball, multiplied by what's the distance here, 0.40. So what I'm going to get, the weight of the ball is actually equals to 1 times 0.25 divided by 0.40. So the weight of the ball will actually be equivalent to 0.625 Newton. Now, do take note, we are looking for the mass of the ball. This is the weight of the ball, so they are different. So exactly now, how to find the mass of the ball? So we know W equals to mg, which means that 0.625 must be equals to the mass of the ball multiplied by 10. So the mass of the ball is actually equals to 0.625 divided by 10, which is the mass of the ball is equals to 0.0625 kg, and this is equals to 62.5 grams. Okay, final answer must be in grams. So take note of the units that they require of you. Okay, otherwise you get it wrong. Now part B, explain why the mass of the ruler play no part in the calculation. To be more precise is why does the weight of the ruler play no part in the calculation in part A. So the weight of the ruler, okay, bracket, its line of action of, okay, its line of action. Now what exactly is the line of action? So every single force has this thing called the line of action of the force. So if the weight is here, the line of action, and let me use a different color to show you, okay, will just be along the force. So this dotted line here is the line of action of the weight of the ruler. For this 100 grams here, to get everyone's idea of what's the line of action, right? So line of action, it will be along the force also. So every single force has this thing called the line of action. Now, so you can, so as long as you draw the line of action, you'll know whether it will be able to cut in through the pivot or not. So the weight of the ruler, okay, the weight of the ruler actually cuts through the pivot. So what is the impact when the line of action cutting through the pivot? When the line of action of the force cuts through the pivot, its perpendicular distance from the pivot is actually 0. Okay? Hence, using using moment equals F times D, its moment generated will be 0. Because why? Anything multiplied by 0 obviously will become 0. Okay, so that's for part B. Now the last one, it says determine the reading on the spring balance. So this is the part where it gets a little tricky. Why I say a little tricky is that, you really tell me this spring balance don't contribute to the moment, how to find? So this is where, when you are looking at the word balance, most of you only see in terms of resultant force, right? The resultant moment. But actually there's the idea of resultant force equals to 0. What does it mean? It means that because I know resultant force is 0, hence, upward forces must be equals to the downward force. So the upward force is actually the force of the spring balance. It must be equals to the downward force generated by this 3. So I know the weight of this 100 gram is 1 Newton. The weight of the ball is 0.625. The weight of the ruler is 1.2. So spring balance will be 1 Newton plus 0.625 plus 1.2. So if you were to do your math, what you're going to get is 2.83 Newton. So the reading here, I'm going to get is 2.83. Teacher, 3 marks just like that. Yes, because actually the weight of the ruler, you're not supposed to have calculated it yet. So in actual fact, this is not 1.2. This is supposed to be 0.12 multiplied by 10. Okay? So there are quite a fair bit of calculations that's involved here that is hidden. So there's this concept of knowing the resultant force is 0. Next, you need to calculate the weight of the ruler. Next, you need to add them all up, knowing that this is equivalent to the force of the spring balance. Okay, so that's for part C. Now, question 5. A heater is rated 230 volts and 3.5 ampere. State the current in each conductor during normal operation of the heater. So to understand this question, okay, you need to know how the diagram generally looks. So think of it as this is a live wire, this is a neutral wire. The current, this is the heater here. Okay, so in typical operation, the current will flow from the live wire to the appliance and out from neutral wire. So you can see the whole thing here is in series. So if the heater is rated 230 volts, 3.5 ampere, it means that in normal operation, it needs 3.5 ampere of current. The voltage across it will also be 230 volts. So if the current going in is 3.5, so we know this 3.5 ampere. And because this is a series circuit, we know that the current coming out must be 3.5. So the question is, what exactly is the rating on the earth wire? So the earth wire is actually connected to the metal casing of the heater. Okay, so this is the earth wire here. And in typical operation, the casing is not supposed to have any current flowing through it. Okay, so that's why the earth wire is actually 0 ampere. In normal operation, the earth wire has no current flowing through it. Okay, the only time when current is flowing through it is when there's a fault, when the live wire, okay, is actually touching the casing. So in actual fact, okay, let's say the heater, this is the coil, then comes out. So the casing here actually is not touching the coil, not touching the wire. It's just wrapping around the whole thing. But once there's a little bit of wire touching the casing gets live. That's where the current actually starts to flow out of the casing through the earth wire. Okay, as such, then that's where you will expect some current, or I should say quite a fair bit of current flowing through the earth wire. Okay, so I need you to take note. Earth wire typically in normal operation is 0 ampere. Whereas the live and the neutral should have the same amount of current because the current going in should be equal to the current coming out. Next, question 6. Figure 6.1 shows a 9.0 volt battery connected to 2 resistors and 1 light bulb. 2 resistors, 1 light bulb. Before we start off, so this is a 9 volt battery. So if you have this long terminal, this short terminal, we can take it as this long terminal will be 9 volts, this short terminal will be 0 volts. One thing I always tell my class to establish is where exactly is the 9 volts until. So take note, voltage is about the amount of energy that each charge carries. It will only be converted away when it passes through a component such as, or I should say a load, such as a resistor, a light bulb, where the energy is converted to other forms of energy. So you look at along this whole wire here, that the charges will not pass through any load. So therefore, the voltage at this point will be 9 volts. Same here, 9 volts. Okay, because energy is not converted to any other forms. So therefore, the voltage across here is 9 volts. Why it doesn't split? Because energy per charge, okay, is about energy per charge. So as long as the energy is not lost because it hasn't gone through a single load, the voltage actually doesn't change. Same thing, if this whole thing is 0 volts here, that means energy has all been used, finished, okay, which means along here, this part here must be 0 volts. Okay, because it cannot be down here 1 volt, right? If this is 1 volt, then how did it become 0? There's no load in between here. So same concept, so if this is 0 volts, anything along this wire before the load, okay, is all 0 volts. Why is it important to establish this? Because if I know this is 9 volt, this is 0 volts, if I put a voltmeter here, what is the reading here? You see the voltage difference, the potential difference is actually 9 volts. Same thing, if I were to put a voltmeter like this, the potential difference here is actually 9 volts. Okay, so once I know that this is 9 volts, this is 9 volts, they ask me to calculate the current through the 6 ohm resistor. Now, the 9 volts is actually across the 6 and the 3 ohm together. So I can't use V equals to IR and say, oh, V is 9, R is 6. So the only one that I know is that the voltage across the 6 and the 3 is 9. So 9 is equal to the current across the resistor of the 6 plus the 3. Okay, so yep, so the voltage is across both of them, hence I must use the resistance of both. And because it's in series, I can just add the resistance up. Hence I know the current is actually 9 over 9. So my current across the down here, which is the 6 plus the 3, is actually 1 ampere. Now, because this is a series circuit, which means that I know the current coming in here is 1 ampere. So what does it mean? It means that the current flowing through 6 ohm and 3 ohm, this is 1 ampere. Once it flows through finish, the current still stays the same 1 ampere. When it reaches here, it is still 1 ampere. So what I can establish from this is that since the I of 6, since 6 ohm resistor and 3 ohm resistor are in series, therefore the current flowing through both of them are the same. So this would mean that the current flowing through the 6 ohm resistor will also be 1 ampere. Okay? Now do take note, final answer always leave to 2 or 3 significant figure. So therefore I put 1.0 over here. Next, calculate the time taken for the charge of 2 coulombs to flow through the 6 ohm resistor. I need the time taken, is T. I will know the charge is given to me Q. When you realize that, hey, this formula here, not my V equals IR, right? No. Actually, you're using the I equals to Q over T. Okay, I equals to Q over T. So the current that I have is 1.0. The charge that I have is 2.0. And the time taken is what I want to find. As such, T is actually equals to 2.0 over 1.0. So the time taken is actually 2 seconds. Right? 2.0 seconds. So just take note of this. Okay. Next one. Question 7. Figure 7.1 shows 3 different containers A, B, C. Each is filled with hot water at 90 degrees Celsius. So we know that all has the same temperature, which is 90 degrees Celsius, 90 degrees Celsius, 90 degrees Celsius. What's the idea behind them? A and B are the same size, C is smaller. So in terms of size, A, B is the same, C is smaller. A has a shiny silver surface. Okay, they say B different from A. How different? Okay, we do not know yet. But let's go on. C has a similar surface to B. So these two, same type of surface. So part A. Container B radiates heat at a higher rate than container A. So B radiates at a higher rate. So key idea, radiation. So there's the mode of heat transfer. And we see the word shiny and silver, we know that, okay, most likely this is a radiation question because only such terms are used in radiation. So how can B radiate heat at a higher rate than A? So I must think in terms of what's the opposite of shiny, what's the opposite of silver. Hence, most probably I can suggest that B has a dull surface. Okay, that's the first suggestion because opposite of shiny is dull, opposite of silver. So B has a black surface. Okay, so I say, sure, how about rough? Can I use the idea of rough? So my question to you is, if A is shiny and silver, okay, did it say that it is smooth? Because opposite of rough is actually smooth. So the question is, so can it be smooth? So to me, it's always important to take note of what term is given to you first. So shiny opposite is actually dull. Silver opposite is actually black in terms of the emission of heat via radiation. So take note of that. Now, part B. State whether C radiates heat at a higher or lower rate than container B. Explain your answer. So C is smaller. We know one of the factors about radiation is about the surface area. So if surface area increase, we know that the rate of the emission, okay, the rate of radiation actually also increases. So what can so we know that C is a smaller exposed surface area. Okay, so it has smaller exposed surface area compared to B. It has one compared to B. So it will radiate heat at a lower rate. So just take note of this. Okay, so that's for part B. Part C here, so infrared radiation is a component of EM waves. Take another component of the EM wave spectrum that's a longer wavelength than infrared radiation. So this one, you remember your whole series here, so it's radio wave. Okay, so those of you who know the song that I show you, so it's radio wave, microwave, infrared radiation, visible light, ultraviolet, X-ray, gamma ray. Okay, so based on this, what you realize is that so longer wavelength, we know that radio wave is the longest wavelength. Okay, gamma ray actually has the shortest wavelength. Shortest lambda, longest lambda. So therefore, infrared radiation, I want something that's longer, so I need to have two possible answers only. So it's either you give me radio wave or you give me microwave. Okay, next. Define electric field. So electric field, this one is a purely textbook definition. So what exactly is the definition over here? Okay, so electric field, it is a region in which an electric charge experiences an electric force. Okay, so this is the purely textbook definition answer. So 1 mark, just like this. Now, part B. Figure 8.1 shows an isolated negative charge. Draw the electric field lines due to the charge. So, the electric field lines, if it's a single charge, it's actually quite simple to draw. Please use your ruler to draw this. I'm just using freehand to draw for speed's sake. Okay, so it will radiate outwards. My general take is always to draw up, down, left, right, diagonal left, diagonal right, stuff like this. Okay, so now next really is about after you've drawn the pattern. Okay, so the pattern, the next part you must draw in terms of the direction. So take note, negative, it will always point inwards. So negative is pointing inwards. So therefore, this is the answer. Next one, part C. An uncharged magnetized iron rod is held close to a negatively charged rod, as shown in figure 8.2. Explain why the uncharged magnetized iron rod experiences an attraction to the negative charged rod. I need to take note here. First thing, this is a magnetized iron rod. Okay, they said it's a negatively charged rod. This one here, you do not know what's the material. Okay, so you do not know what's the material, but you know iron rod is magnetized. You can't really conclude. Okay, you cannot say that must be this one is this one must be iron or steel, nickel, and cobalt. This one attract. Okay, that's inference you're making, which is actually not true, because you do not know. Okay, so hence this question is actually not about magnetism. Again, it's really not about magnetism. The magnetized iron rod here is just there to confuse you only. The key focus here is still on electrostatics. Okay, electrostatics. Now, this is a negatively charged rod. What's going to happen is that it will repel, because iron, this is iron. So because this is iron, this is a metal, you know that they have free electrons. Okay, so this is the key idea you need to take note of. So if I got a negative charge rod brought here, what's going to happen is that the free electrons, which are the negative charges, are going to move to this side. Okay, so if I got 5 electrons resulting, if the general idea is that because the electrons are repelled over to this side, so I got 5 negative charges over here, hence the resulting part here, I'll have 5 positive charges. Okay, and because this is negative, this is positive, what's going to attract here? What's going to happen here is that you know that it will attract. So this is actually the general idea of what's happening here. So how do you exactly put down words? So first thing, you're going to say that the negatively charged rod, so negative charged rod, okay, actually repels. Take note, repels what? The electrons. Or if you put negative charge, I think that should be fine also, but repels the electrons in the rod, or electrons in the iron rod, and I'm just going to put iron rod, iron rod to the side further away, to the side furthest away from the negatively charged rod. I realize I'm repeating myself, but you get the idea, negatively charged rod. Okay, so all the negative charge comes here. So what happens next is that this actually induces, or if you use the word results or creates. Okay, actually I don't like the word create, causes. Okay, but actually the keyword here you should be using is inducer. Causes the site nearer to the negatively charged rod. This causes the side of the iron rod nearer to the negative charge rod to be positive. Okay, so we're trying to say negative charge come here, hence down here become positive. Hence, since unlike poles attract, unlike charges attract, because none of these charges are, since unlike charges attract, okay, therefore, the rods will be attracted to each other. The rods will be attracted to each other. Okay, so that is the answer to this part over here, part C. Okay, question 9. Figure 9.1 shows a trolley in a stationary position. So stationary, not moving. Okay, figure 9.1, draw all the forces acting on the trolley. Now, this is the question that some of you say, friction. Do they know it's a stationary position? So there's no friction. Experience this because it is not moving. Because take note, friction opposes motion, or is a force that opposes motion. Right now, there's no movement here, hence we do not need to talk about friction. First thing, for any single object, because it has mass, it will have weight. So we must first locate the center of gravity. From the center of gravity, we draw one line down. What exactly is this? This is the weight, okay, of the trolley. Now, as long as an object is in contact with something, we have this idea called the contact force. Okay, so the contact force always acts in perpendicular to the surface. So if this is the surface here, my weight is downwards, the contact force will actually be opposite of it. So it's a vertically upward line. Because there's 2 points of contact, so this is actually the contact force. This is also the contact force. Now, the contact force is actually what we call a normal reaction force. It's actually a reaction force that acts normal to the surface. Normal means perpendicular. Okay, so weight here, and then the 2 contact points draw perpendicular to the surface. That's called the contact force, and this will be the answer. Okay, excluding this part, this one is actually just by additional labeling. Okay, so it's actually just this part over here. Okay, next, part B. Okay, what exactly is part B talking about now? Trolley X and Y are joined together by a stretch spring. Okay, shown in figure 9.2, and X and Y have a mass of 4 kg and 2 kg respectively. So this 4 kg, this 2 kg. So we know the mass of Y is half of X, or I should say the other way around, X is twice of Y. So when the trolleys are released, the initial acceleration of X is 2 meters per second squared. So we know the acceleration will most probably be this side, and the value is 2 meters per second squared. Calculate the force experienced by trolley Y. So force, I got acceleration, simple sure, F equals to ma. So the force that I'm going to be experiencing is actually 4 multiplied by 2, 8.0 Newton. Okay, quite a simple 2-mark answer here. Without using any calculation, explain why acceleration of trolley Y is twice of trolley X. Okay, key idea here, because both of them are connected by the same spring, hence the force experienced is the same. because the force experienced by X is because of the pull of the spring. Y is also by the pull of the spring. And do take note, because it's the same spring, the force experienced by both of them, or the force of the spring, is the same. Okay, force of the spring is the same. So without using any calculation, explain why acceleration of Y is twice that of X. So first thing you must establish is that the force experienced by trolley X and Y is the same. You don't need to go into further details. You can just tell me this. There'll be one part to the answer. Next, using F equals to MA. Okay, since mass of X is twice of Y, comma, therefore the acceleration, okay, maybe I should not put twice up, the mass of Y is half of X. So we use Y as the subject of as a key point, is half of X. Therefore acceleration of Y is twice of X. So key idea here, if this is the same, if my mass is halved, to compensate for it, my acceleration must be double. So I say again, if my force is the same for X and Y, but one of them, the mass is halved, the acceleration needs to be doubled to compensate, to make sure that I get the same amount of force. Okay, so that's for question 9. Now question 10. A coil is wound on an iron core. It is placed near a permanent magnet as shown in figure 10.1. Okay, explain why the permanent magnet moves away from the iron core when the current is switched on. So this part here, okay, so what's the question is asking, explain why the permanent magnet moves away from the iron core when the current is switched on. So first things first, we know this is a magnet. What's going to happen when I got a coil around an iron core when I switch on the current? We know that the current will flow in this direction. Okay, so if I have a coil around an iron core, what I'm going to do is I'm going to cause it to become an electromagnet, and hence there will be magnetic poles induced on the iron core. So first part, when the circuit is switched on, okay, the iron core becomes an electromagnet. Now, so what if it has become an electromagnet? Why does it exactly repel? It moves away, it's actually repulsion. Why does it repel? When the circuit is switched on, iron core becomes an electromagnet using you must write it out, but I'm just going to write RHG. Using the right hand grip rule, okay, but it's right hand grip rule, please spell it out. The side nearer to the magnet, the side of the iron core nearer to magnet will become a north pole. How do you know? If you use the right hand grip rule, you realize that this is a north, this is a south. Okay, so once you know this is a north pole, right, it's quite immediately you know, right, since like poles repel, okay, like poles repel, hence they will move away from each other. Okay, they will move away from each other. Okay, so that's for the first part. Next, a permanent magnet is replaced by an iron rod. Right, permanent is replaced by an iron rod. So instead of having a permanent magnet here, now it's just an iron rod. Okay, so this is an iron rod. Now what exactly will happen next? Okay, when the current is switched on. So the first part is still the same thing. So iron core becomes electromagnet. And using the right hand grip rule, the side nearer where the side of iron core nearer to the iron rod, nearer to the iron rod will be a north pole. Now this is where the explanation starts to get a little bit different. At this particular point, because it's an iron rod, what we can conclude, magnetic induction will occur, right? Will occur, causing the left side of the iron rod to become a south pole. So what exactly happened? So once again you got a north pole over here, but when this become a north pole and this is an iron rod, this north pole will actually cause the left hand side here of the iron rod to become a south pole. Okay, this is what exactly we are talking about here. And then the last one is, since unlike poles attract, hence the rods will move closer, or they will attract. Okay, so that's for this part B over here. So that's all for this whole section A. If you got any questions, please feel free to ask the teachers. Okay, that's all from me. Thank you.